All right, let's continue our look at classification of quadrilaterals in Euclidean geometry. Now, one of the ways, well, actually, there's many ways we can look at quadrilaterals, and an interesting exercise is just to decide how many ways can you classify them. And I think I've come up with, if not all of them, pretty close to it in this big GeoGebra activity here. So one of the things we could do is look at, do we have any sides that are congruent? Well, the first way we could do it is to have something with no sides congruent. Okay, and this I will call it like after the version that we have in for triangles, we'll call this a scalene. Now, to do this so that it would always work, I've got this set up with the shortest side being the blue one, S1, AB, S2, BC is the next longest side, then S3 for the next side, and then S4. And notice once I fix those sides, there's definitely some ways we can move some of these around. Of course, B moves around A in a circle. Of course, you can mess it up where it's not a quadrilateral at all like that. But you know, some of these are convex. There's a concave one there. Um, so you can see some examples of some scalene quadrilaterals. None of the sides are the same length. Now, next thing we can do is at least one pair of congruent sides. Now, it makes a difference whether those sides are opposite each other or congruent each other. So we're going to have two cases here. Here's one where we have a pair of opposite sides congruent. Now, notice some basic figures have this characteristic, like rectangles. In fact, all parallelograms have opposite sides congruent. Isosceles trapezoids as well. But it's definitely be able to make this so that there are no parallel sides. Um, and so that we can get we may maybe concave like that, maybe convex. This includes somewhere in here I could adjust it so that we do get somewhere in here that's a parallelogram. Somewhere in here it might be, depending on where I end up with this, it could possibly be an isosceles trapezoid. Let's see if I can get there. I don't know if I can get there or not. I need to make these things parallel. Yeah, no, not there. Okay, but anyway, you see the idea. We can get lots of different things here. But this shows you that a pair of opposite sides congruent's not enough, say, to make it an isosceles trapezoid or a parallelogram. What about a pair of congruent sides that are consecutive, like AB and AD? Okay, and so that this other side, you know, there's lots of different places it could go. And you see that it's not necessarily a kite, even though a kite would have that property. Now, if it has two disjoint pairs of consecutive sides, it is in fact a kite. That's the definition of it. And we study kites in some detail. If you take a diagonal here, you get a reflective symmetry. So triangle ABC is congruent to triangle ADC. That makes a lot of cool things happen, including having the line containing, well, it gives you a mirror line of symmetry here, and the line containing the major diagonal is a perpendicular bisector of the minor diagonal. And so we have these properties of a kite. By definition, a quadrilateral is a kite if and only if it has two disjoint pair of consecutive congruent sides. Turns out the major diagonal has endpoints where the congruent sides meet. The other diagonal is a minor diagonal. A convex kite is also known as a dart. A major diagonal and the sides form two congruent triangles. Specifically in the diagram, triangle ABC is congruent to triangle ADC. It has reflective symmetry about the line containing the major diagonal. The major diagonal is part of an angle bisector at both ends. So angles here is bisected, the angle here is bisected. So that's cut in half. That angle is cut in half there or there. Let's see where else. The minor diagonal sides form two isosceles triangles, one there and one there, not necessarily congruent. They might be congruent, but not necessarily. The line containing the major diagonal is perpendicular bisector to the minor diagonal. The diagonals of sides form two smaller pairs of congruent right triangles. So if we look at the line containing the major diagonal and the minor diagonal there. We've got a triangle, let's see, I guess ABX is congruent to triangle ADX, and triangle BCX is congruent to triangle DCX, and right angles all the way around at X. These are following our equivalent conditions. Quadrilateral ABCD is a kite with the length of AB is equal to length AD, and the length CB is equal to length CD. That's true if and only if quadrilateral AB has triangles ABC congruent to triangle ADC. That's true if and only if quadrilateral ABC with AC, line AC being a perpendicular bisector of the minor diagonal BD. That's true if and only if you have a quad ABCD that has reflective symmetry about line AB. That's if and only if a quadrilateral ABCD with a major diagonal AC being an angle bisector on both ends. That's if and only if quadrilateral ABC has a major diagonal AC being an angle bisector on one end and it's perpendicular to the other diagonal. And that's if and only if quadra ABCD with major diagonal AC being an angle bisector on one end and AC bisects line segment BD. So any one of those conditions is enough to get all of them. So lots of cool properties of a kite. We can also have two opposite sides congruent. That turns out to be a parallelogram. One of the things that we can prove, and we have proved, is a quadrilateral is a parallelogram if and only if both pairs of opposite sides are congruent. Now, a parallelogram has lots of cool things. For one thing, opposite angles are congruent. These two angles at B and D are congruent. The interior angles at A and C are congruent. And if you take any consecutive pair, say A with D or A with B, or B with C, or C with D, any of those pairs that are consecutive are supplementary. It turns out that the diagonal, if you take one diagonal, it makes two congruent triangles with the rotation. Or if you do the other diagonal, same thing. Turns out the diagonals then intersect each other at the midpoint of each other, so they bisect each other. And these four little triangles are two pairs of congruent triangles. So you get a little triangle here and here that are congruent. Specifically, DX is congruent to CBX. And then similarly, you got a triangle on this side and this side here that are congruent as well. There's lots of different equivalent conditions for a parallelogram. Any one of these is enough to make it a parallelogram. Okay, triangle ABC is congruent to triangle CDA inside of quadrilateral ABCD. Triangle AXB is congruent to triangle CXD, where X is the intersection of the diagonals, or you could just say it's the midpoint of one of the sides that you have, one of the diagonals that you have. Or you could say triangle AXD is congruent to triangle CXB, or that the quadrilateral is a parallelogram, or that both pair of opposite sides are parallel, that is the definition of parallelogram, or that both pair of opposite sides are congruent, not the definition of a parallelogram, but one of the properties, and at least one pair of opposite sides are congruent and parallel, or the diagonals bisect each other. If you have any one of those properties, you can prove that it has all of them. And we spent some time on that earlier. Now, what about if we have more than two congruent sides? So what did we start with? No congruent sides, one pair that was opposite, one pair that was consecutive, two pair that are consecutive that don't overlap, two pair that are opposite, and then the other way is you could get three. And by the way, this is why we have to say on a kite two disjoint pairs of consecutive congruent sides, because we have a pair of congruent sides AB and AD, and another pair AB and BC are congruent, but we don't want that to be a kite. So that's why we need the word disjoint there. But here's one where we have three congruent sides. A special case of that would be this one here, an isosceles trapezoid with congruent sides, three congruent sides. And we talked earlier about pattern blocks. There's a pattern block that looks like this if you just get the correct angle. If you get a 60-degree angle right there, then there's a pattern block that's this kind of a figure. And if you get 4 congruent sides, that's a rhombus. A rhombus has lots of cool properties. Okay. If you take a diagonal, it has symmetry about that diagonal and about the other one. The diagonals are perpendicular bisectors of each other. They will intersect, so it is a convex interior, convex quadrilateral. The 4 little right triangles that you see here are all congruent to each other. Both diagonals are angle bisectors on both ends. Okay. It turns out that the area is 1/2 the product of the length of the diagonals. And so the following are equivalent. It's quad ABCD is a rhombus. It's equilateral. That's the definition. Or if you can say both diagonals are perpendicular bisectors of each other, that's enough to make it a rhombus. And if you get ABC is congruent to ACB, is congruent to CBD, those are all triangles that are congruent, that's enough. And if quad ABCD is a parallelogram with perpendicular diagonals, that's enough to make it a rhombus. So there are several ways to classify quadrilaterals based on the number and position of their congruent sides.